This battery was nearly forgotten, lost in the dusty archives of old patents and overlooked by today's engineers. It wasn't explosive, flashy, or groundbreaking, but it had one remarkable quality: it never truly died. Now, as lithium dominates the spotlight, this old technology is quietly making a comeback. Zinc-Bromine, a chemical combination from the 1800s, isn't here to power smartphones or electric cars. Instead, it's stepping up for something far more critical: large-scale energy storage. It offers safety without the risk of flames, simplicity without cutting corners, and longevity without a high price tag. So, why is this forgotten design suddenly being taken seriously? The answer lies in the limitations of the very batteries we rely on today. Lithium-ion batteries have undeniably shaped modern life, powering everything from gadgets to electric vehicles. They're compact, efficient, and seem unstoppable at first glance. But beneath their sleek surface lies a growing list of problems. Mining lithium is an environmentally destructive process, consuming 500,000 gallons of water per ton extracted. In regions already battling drought, this is nothing short of devastating. The demand for lithium keeps climbing, and so does its price, spiking over 700% in China in just 1 year. These rising costs ripple through industries, affecting car manufacturers, renewable energy projects, and consumers. Then there's the issue of safety. Lithium batteries can overheat, ignite, and burn uncontrollably. Some fires rage for days, releasing toxic fumes that force evacuations. Recycling them remains a complex and hazardous challenge. Despite these flaws, lithium remains the dominant choice, not because it's perfect, but because alternatives have fallen short. Until now. An older, overlooked battery chemistry is re-emerging as a viable solution. Zinc-Bromine batteries were first patented in 1885 but spent most of their existence in obscurity. They were considered too bulky, too niche, or simply too unconventional. That perception is finally shifting. At their core, zinc-bromine batteries operate on a fundamentally different principle than lithium-ion. They're a type of flow battery, relying on liquid electrolytes stored in separate tanks. One tank holds zinc ions, the other contains bromine. These liquids are pumped through a cell stack, separated by a membrane where they exchange electrons to generate electricity. Charging simply reverses the process. The design is inherently scalable. More cells mean more power, larger tanks mean more storage. Unlike lithium, these batteries don't rely on tightly packed solid materials, eliminating the risk of thermal runaway. Your electrolytes are water-based, non-flammable, and stable. They can be fully discharged without degrading over time. Zinc-Bromine stands out as one of the most promising flow battery variants. It uses abundant, inexpensive materials and stores energy safely for long durations. It could be the ideal solution for storing solar and wind energy if someone could make it practical. That's where companies like Gelion are stepping in. Instead of sticking with the traditional flow battery setup, pumps, pipes, and tanks, Gelion reimagined the chemistry. Their battery, called Endure, replaces liquid electrolytes with a thick, stable gel. This gel is sandwiched between zinc and bromine plates, housed in a casing similar to lead-acid batteries. The similarities end there. Inside, it's a completely different system. No lead, no sulfuric acid, just a fire-resistant gel that safely conducts energy. Even more impressive, Gelion's manufacturing process leverages existing lead-acid battery factories. Out of 22 production steps, 18 can be done with current equipment. No billion-dollar gigafactories needed, just smarter use of what's already available. The result is a compact, rugged battery that's already being produced at scale. A 137-year-old chemistry revived without the complications of its original form. Meanwhile, companies like Redflow are embracing the traditional flow battery approach but refining it for modern needs. Their ZBM3 battery uses liquid electrolytes, pumps, and tanks, but with a focus on resilience. Built for harsh environments, these batteries thrive where lithium would fail. Telecom towers in the Australian outback, off-grid homes, and industrial microgrids all benefit from their durability. Each Redflow unit stores 10 kilowatt-hours and is designed for full daily cycling. Unlike lithium, it can be completely drained and recharged every day without damage. It operates in scorching temperatures up to 45 degrees Celsius without external cooling. It even self-cleans through a process called a strip cycle, preventing zinc buildup. In 2023, Redflow began mass production in Thailand and expanded into North America. Their strategy targets places where the grid is unreliable, diesel is expensive, and safety is non-negotiable. It's old technology, but it works where modern alternatives can't. Safety is where zinc-bromine truly outshines lithium. When lithium batteries fail, they do so catastrophically. Fires, explosions, and toxic fumes. A single damaged cell can trigger a chain reaction, destroying entire systems. We've seen it happen. Tesla megapack fires burning for days, requiring specialized firefighting efforts. Zinc-bromine avoids all of this. Its water-based electrolytes won't ignite even under extreme stress. Gelion's gel formulation takes safety further. It resists fire and may even suppress it. Bromine, ironically, acts as a natural flame retardant. In demonstrations, Gelion's battery continued functioning even while scorched at 700 degrees Celsius. Vanadium flow batteries offer similar safety but come with their own risks. Vanadium oxide is toxic and its electrolyte is highly corrosive. Zinc-bromine isn't flawless. Bromine is hazardous if mishandled, but it's stable and easier to detect. In a world where energy storage risks are a growing concern, this reliability matters. Cost is another area where zinc-bromine excels. Vanadium flow batteries require expensive materials with chemical costs around $124 per kilowatt-hour. Zinc-bromine, by comparison, costs just $8 per kilowatt-hour for raw materials. System-wide, the savings are even more dramatic. A 2021 analysis found zinc-bromine systems averaging $153 per kilowatt-hour in material costs. Vanadium systems, by contrast, came in at $491. Zinc-bromine also skips the need for expensive cooling, fire suppression, or custom enclosures. Gelion's use of lead-acid battery casings cuts manufacturing costs even further. Retrofitting a lead-acid factory for zinc-bromine production costs around $16 million. Building a new lithium-ion factory? That's closer to $130 million. Installation is simpler too. Less bulk, fewer safety concerns, and lower engineering demands. For grid-scale storage, these efficiencies add up fast. Performance is where zinc-bromine proves its worth. Redflow's batteries last over 4,500 cycles. Gelion's Endure surpasses 5,000. That's more than double the lifespan of most lithium-nickel systems. Even lithium iron phosphate LFP batteries rarely exceed 20,000 cycles. Round-trip efficiency is strong, with Gelion reporting 85 to 90%, rivaling lithium-ion. Temperature tolerance is unmatched. These batteries operate in extreme heat without cooling. They're already deployed in deserts, remote sites, and fire-prone areas. No lab tests, no prototypes, real-world use, day after day. Zinc-bromine isn't a one-size-fits-all solution. It's too heavy for electric vehicles, too bulky for consumer electronics. But where it fits, it excels. Long-duration storage, renewable energy buffering, remote infrastructure. It handles heat, deep cycling, and harsh conditions without flinching. Dendrite growth, a common issue, is mitigated by Redflow strip cycles and Gelion's membrane design. This battery has limits, but it fills a crucial gap. Lithium will keep its place in mobility, but zinc-bromine is carving out its own niche. The future of energy storage won't rely on a single technology. It'll be a mix, with each chemistry playing to its strengths. Zinc-Bromine may not be flashy, but in a world demanding safe, durable, and affordable storage, it's exactly what we've been missing. A 19th century idea reborn for the 21st century grid. The resurgence of zinc-bromine batteries isn't just a fluke, it's a response to a critical need in energy storage. While lithium grabs headlines, the limitations of our current systems are becoming impossible to ignore. Zinc-bromine offers a path forward, one that balances performance, safety, and sustainability. But to understand its potential, we need to look beyond the technical specs and into the real-world challenges it can solve. One of the biggest hurdles for renewable energy is intermittency. The sun doesn't always shine, and the wind doesn't always blow. Storing excess energy for later use is essential, but lithium batteries aren't always the best fit for long-duration storage. They degrade with deep cycling, lose efficiency in extreme temperatures, and come with fire risks. Zinc-bromine, on the other hand, thrives in these scenarios. Its ability to discharge completely without damage makes it ideal for daily cycling. Solar farms, for example, generate power during the day, but need to store it for nighttime use. With zinc-bromine, that energy can be stored and released without worrying a battery wear. Wind farms face similar challenges. Unpredictable generation requires reliable, long-lasting storage. Zinc-bromine's durability and scalability make it a natural fit. Then there's the issue of infrastructure. Many remote communities rely on diesel generators for power, which are expensive and polluting. Replacing them with renewable energy requires storage that can handle harsh conditions. Zinc-bromine batteries, with their tolerance for heat and lack of cooling needs, are perfectly suited. Redflow's deployments in the Australian outback prove this. Their batteries power telecom towers where lithium would fail. Off-grid homes and microgrids also benefit from this resilience. In places where the grid is unreliable or non-existent, zinc-bromine provides a stable, low-maintenance solution. The environmental advantages can't be overlooked either. Lithium mining devastates ecosystems, depletes water supplies, and leaves behind toxic waste. Cobalt, another key lithium battery component, is often mined under unethical conditions. Zinc and bromine, by contrast, are abundant and easier to extract responsibly. Zinc is widely recycled, and bromine is a byproduct of seawater processing. This makes zinc-bromine batteries a more sustainable choice from start to finish. Even at the end of their life, they're easier to handle than lithium batteries. Recycling lithium is complex and hazardous, but zinc-bromine components can be separated and reused more efficiently. The economic implications are just as compelling. As renewable energy expands, the demand for storage will skyrocket. Lithium's supply chain is already strained, leading to volatile prices. Zinc-bromine, with its simpler materials and lower costs, offers a stable alternative.
This could make renewable energy projects more financially viable, especially in developing regions. The ability to manufacture these batteries in existing lead-acid factories is another game-changer. It reduces upfront costs and speeds up production scaling. For countries looking to build local energy storage capacity, this is a major advantage.
No need for expensive, specialized facilities, just retrofitted factories and a ready workforce. This democratizes access to advanced energy storage, leveling the playing field. But zinc-bromine isn't just for large-scale projects, it's also finding a place in residential and commercial storage. Homeowners with solar panels need reliable batteries that won't catch fire or degrade quickly. Businesses looking to cut energy costs want storage that can handle daily cycling without maintenance. Zinc-bromine meets these needs without the risks of lithium. Gelion's Endure battery, for example, is designed to drop into existing lead-acid setups. This makes it an easy upgrade for homes and businesses already using solar storage. The safety factor alone is a selling point. No one wants a battery that could burn down their house. The industrial sector is another promising market. Factories and data centers require uninterrupted power, often relying on diesel backups. Zinc-Bromine batteries can replace these generators, providing cleaner, quieter, and more reliable energy. Their ability to operate in high temperatures means they can be installed in demanding environments. Data centers, which consume massive amounts of power, could particularly benefit. The risk of lithium battery fires in server farms is a growing concern. Zinc-bromine's non-flammable chemistry eliminates that threat. Even the military is taking notice. Reliable, safe energy storage is critical for field operations. Zinc-bromine batteries can power remote bases, communication equipment, and mobile units without the risks of lithium. Their rugged design and temperature tolerance make them ideal for harsh environments. This versatility underscores the broader potential of zinc-bromine technology. It's not just a niche solution, it's a viable alternative for a wide range of applications. Of course, no technology is perfect, and zinc-bromine still faces challenges. Energy density is lower than lithium, meaning these batteries take up more space for the same capacity. This makes them less suitable for applications where size and weight are critical, like electric vehicles. But for stationary storage, where space is less of an issue, this trade-off is acceptable. Another challenge is public awareness. Lithium dominates the conversation. So many people don't even know alternatives exist. Changing that perception will take time and education. Companies like Gelion and Redflow are leading the charge, but broader adoption requires industry and policy support. Governments can play a role by incentivizing safer, more sustainable storage solutions. Funding for research and pilot projects could accelerate development. Streamlining regulations for non-lithium batteries would also help. The good news is that momentum is building. Investors are starting to recognize the potential of zinc-bromine and other alternative chemistries. The energy storage market is vast enough for multiple technologies to coexist. Lithium will continue to dominate portable electronics and EVs, but zinc-bromine can carve out a significant share in stationary storage. This isn't a zero-sum game. Diverse solutions are needed to meet diverse needs. Looking ahead, the next decade could be a turning point for zinc-bromine batteries. As renewable energy adoption grows, so will the demand for reliable, long-duration storage. Lithium alone can't meet that demand, especially as its limitations become more apparent. Zinc-bromine offers a proven, scalable, and sustainable alternative. It's a technology that was ahead of its time in the 19th century, but is perfectly suited for the 21st. The pieces are falling into place: manufacturing innovations, real-world deployments, and growing market interest. What's needed now is the collective will to embrace it. The energy transition isn't just about generating clean power, it's about storing and managing it intelligently. Zinc-bromine batteries, with their unique blend of safety, durability, and affordability, could be a cornerstone of that future. They remind us that sometimes the best solutions aren't the newest or flashiest, they're the ones we've overlooked for too long. So, are zinc-bromine batteries finally getting their moment? The signs point to yes. As the world wakes up to the limitations of lithium, alternatives like zinc-bromine are stepping into the light. They may not replace lithium entirely, but they don't need to. Their role is just as vital, powering the grid, supporting renewables, and keeping energy safe and accessible. In the end, the future of energy storage won't be a single technology, but a mosaic of solutions, each playing to its strengths. And zinc-bromine, the forgotten chemistry of the past, is ready to claim its place in that future.